Hi everyone, how are you doing? Okay, so in this lecture, we are going to start conditional expectation. Like we already have started conditional expectation, but we will see more examples on conditional expectation, and then we will start something called as total expectation. Okay, so let's get started. Okay, so let's see with this directly with this question. So let's see what this question is saying, and then we will try to understand these concepts with the help of multiple questions, right? So let's see this first question. So what this question is saying, that suppose that x is number obtained when you are rolling a die. Okay, now they're asking you what is the expectation of x, what is the expected number given that the number rolled is at least 4, which means it is either 4 or 5 or 6. If it is given, then what is the expected number? Can you think of this question? Can you try to solve this question? See, in the reduced domain, if you see this event, okay, this event as a whole domain, which means if you reduce the domain, so this is the only possibility, right? This is the only possibility. In in these three possibility, what is the average? What is the expected number? It is 4 plus 5 plus 6 divided by 3, right? So you can say, I mean, this is just one way of solving it. It is 4 plus 5 plus 6 divided by 3. How we solve it? Using reduced domain. Okay. So what is the answer, by the way? It is 5, right? Okay. This is using a reduced domain. Okay. Now, if you want, you can solve this question easily with the help of formula also. So what is the formula of expectation of x given, let's suppose, any event, which is, let's suppose, a or x greater than or equal to 4. So what is the formula? Do you remember the formula? So formula of expectation of x used to be summation over all values of x, right? X multiplied by probability of x being x. So the only difference is that here you will be writing x greater than or equal to 4, right? Okay, I mean, it will be given something like this. Yes, great. So Sonam has also written the same formula. Okay, now using this formula, can you guys try to solve this particular question? I mean, we have solved this question using the reduced domain, but now I'm asking you to solve the same question using the using this formula. Okay, so let's just try doing it. Let's just try solving this question using the formula also. Okay, let's just see if we can do it. Now, what are the possible values of x? The possible values of x are basically 1 to 6, right? So it will be 1 into 1 into 1 into probability of x being 1, given that x is greater than or equal to 4. So what is this probability, by the way? Plus 2 into probability of x being 2, given that x is greater than or equal to 4. So if you already know that x is greater than or equal to 4, what is the probability that x is 1? I think this will be 0, right? This is 0. Similarly, this will be 0. Similarly, plus 3, like you will be writing plus 3 and this particular quantity. So you will say this will also be 0. So basically, if you solve this question, then using the formula also, then you will be getting the same thing. X greater than or equal to 4. This is also 0, right? Now, plus 4 into probability of x equal to 4, given that x greater than or equal to 4, plus 5 into probability of x equal to 5, given that x greater than or equal to 4, like that, right? Plus 6 into probability of x equal to 5, x equal to 6, given that x greater than or equal to 4. So what are these probabilities? What is this probability that given that x greater than or equal to 4, okay, what is the probability of x being 4? I think this is 1 by 3, right? This will be 1 by 3. What is this probability? I think again this will be 1 by 3. What is this probability? Again this will be 1 by 3. So finally, it will be 4 plus 5 plus 6 divided by 3, which is just 5 again, right? So you can solve like this also. Okay, both ways are fine. Okay. So little bit about the conditional probability, oh sorry, the conditional expectation you might already be knowing from the last class. Now, we will be solving more questions on the conditional expectation only, but there will be on top of that there will be one more problem which is the total expectation. Okay, so we will be solving questions for the total expectation. But before that, let's just see what is the law of this total expectation. Bit of this we have already touched in the module 1, right? So not very formal, I mean in not very mathematical way, but using the graphical representation of the tree method, right? So we have already seen the tree method of this total expectation kind of thing in the module 1, right? So we have already seen tree method in module 1. By the way, let me just tell you, this tree method that we have taught in module 1 is one of the things that I liked the most in probability. So this was one of my, you can say, the eureka moment for the teaching, that because because that tree method, maybe I think I have told you, or I don't remember I have told you or not, but this tree method was something that actually, I saw few of the question, and then I understood it with the different ways, which means if we expand the tree, if we don't expand the tree to infinity or like that. So I first solved all of these question, I understood all of these theories, because that theory was not given anywhere, in that illustrative way. So there might be question here and there for the tree method and the expectation, but that was not detailed explanation anywhere. So I discovered that detailed explanation by myself, and then I taught it. So I can say this was one of my eureka moment for this module 1 and the teaching. So I really like the tree method. Okay, so now let's just see this law of total expectation. But before that, maybe we can solve one or two more question, and then these question will basically relate to the law of total expectation. Let's just see what this question is saying. So what they're saying, determine the expected number of heads. Let's suppose they're writing it en in n flips of biased coin. So they are saying what is the expected number of heads if you do the n flips. Okay. So how to solve this question? Expected number of heads if you do the n flips. So let's just see this. So let's suppose that en is expected number of heads and n flips. So we can define it recursively like this: that if the first flip is head, then the expected number of heads will be 1 plus e of n minus 1, because in n minus 1 flips, whatever is the heads I'm getting, and then 1 plus that, right? Is this okay to everyone? That if, see, if en is, so if I'm saying that en is the expected number of heads, right? In n flips, then en minus 1 is expected number of heads in n minus 1 flips. So if the first flip is head, then the total heads will be 1 plus whatever is the next time I'm getting, right? If the first flip is tail, then the total number of heads that I will be getting is just the e of n minus 1, right? So you can solve this question like this, and then this en will be very easily, you can say en will be, uh, if it is head, let's suppose with the probability p, then p into the expected number of heads plus q into the expected number of heads, right? So if you solve this, this is okay. So this will be a recurrence relation kind of thing. So let me just tell you that it is en. Yeah. So you are getting en equal to en minus 1 plus p, right? So which means en equal to, you're getting e of n minus 1 plus p. Okay. And then they're asking you to find en. So you can solve this recursively. Maybe okay. I don't know if you have seen the algorithm lectures or not, but if you have not seen then don't worry about it. So basically, what you can do, you can repeatedly substitute. So what is the en minus 1? This en minus 1 will be e of, if you put n minus 1, e of n minus 2 plus p, right? So basically, this En that you have is nothing but E of n minus 1 plus P. So if we put the value of E of n minus 1, then it will be E of n minus 2 plus P. And then plus P, this plus P is already there, right? Plus P. So basically, you can say that this quantity you're replacing by this much, right? You're just replacing n E of n minus 1 with this. So it will be E of n minus 2 plus 2P. So actually, this recurrence relation solving will be there in the algorithm lecture, that how to solve these kind of recurrence. It is just a substitution method. It is easy. It's not very tough, but still, let's just look at it. So basically, E of n is nothing but either En minus 1 plus P or En minus 2 plus 2P, right? Similarly, if you keep on enrolling it, then it will be E of, if it is minus 2, then it is 2P. If you are writing minus n, then it is NP, right? So it will be E of 0 plus NP. So expected number of heads in the 0 flip is just 0. So it is NP. Okay. So basically, what I'm trying to convey here is that if you want to write this En, okay, let's not worry about the solving recurrence relation. But if you want to write this En, it will be probability of head, probability of head into expected number of heads in remaining flip, right? In n minus 1 flips. Similarly, similarly, so basically the first flip, right? The first flip could be head. So probability of first flip to be head, right? This is basically first flip to be head plus probability of first flip is tail, right? In that case, what is the expected number of heads that we will be getting? So this is how you can solve this question. Basically, the expected number of heads will be the expected number of heads. If the first flip is head, then what is the remaining expected number of heads? If the first flip is tail, then what is the remaining expected number of heads, right? Okay, maybe with the more example, it will be more clear. So let's just try to solve this example and let's just see what is the answer we are getting here. Do you want to try this particular question? Let me just tell you what this question is saying, and then maybe you can just try it out, right? Okay. So what this question is saying that a miner is trapped in a mine containing three doors. The first door leads to a tunnel that will take him to a safety after 3 hours of travel. So basically, he's saying that they are saying that there are three doors, right? The first door leads to a tunnel which will take him to the safety after 3 hours of travel. So basically, let's suppose this is door one, this is door two, this is door three. Now this door will get him to the safety after 3 hours. Okay, 3 hours of travel. If he gets to this door, the second door leads to the tunnel that will return him to the mine after 5 hours hours of travel. Okay, so basically he is already trapped in the mine, right? And now they are saying that if the miner enters into this door, then he will just waste 5 hours. So they are saying that after 5 hours he are just returning to the mine. So it is not the safety. Okay, so basically here the miner is returning to the safety, but here the miner is basically returning to the mine only. Okay, uh, returns him to the mine. Okay, so which means it is not leading to the safety. The third door leads to the tunnel, which return him to the mine after 7 hours. So after 7 hours, he just returned into the mine after wasting 7 hours. If we assume that miner is all time equally likely to choose any of the door, then what is the expected length of the time that he reaches to the safety? Can you tell me what is the answer that you will be getting here? So basically, let's suppose that expected number of, they're asking the expected length of the time. So let's suppose expected time after which he will be returning to the safety is ET. Okay. So what it should be, if it chooses door one, if it chooses door one with 1 by 3 probability, then after how much time he will be returning to the safety? If he chooses door 2, then after how much time he returns to the safety? If he chooses door 3, then after how much time he returns to the safety? So you need to write all of these three numbers. So what is this first number? What is this first number? 3, right? So this is basically, you can say this is basically for door 1. This is for door 2. This is for door 3. Okay. So actually, I don't want to solve this question. I want you to solve the question. Just tell me what is the value of D1, let's suppose. What is the value of D2? What is the value of D3? And then we will be solving it further. Okay. So as Diksha and Sonam are saying, the D1 value is 3. Okay. So let's just keep it 3. I think this is 3 only, right? Because after 3 unit of time, he will be returning to the safety. But what is the value of D2 and D3? Can anyone tell me? So I think we have got a couple of the answers. Let's see if they are correct or wrong. Okay. So let's see if D2 is 5 plus ET or not. So this is D2. D2 is a time, basically I'm saying it is a time after which he returns to the safety. Actually, he just waste 5 hours, and after that he just restarting, right? So that's why it should be 5 plus ET. Yes, this is correct. It should be 7 plus ET, right? Okay. So if you solve this, then you will be getting the answer, and the answer is 7 plus this. So ET is EX, or ET is basically 15, right? So on average, after 15 unit of time, he will be coming out, right? This expected number, do you understand what does this expectation mean? How many of you understand the expectation mean? So what does this 15 represent here? Can anyone tell me intuitive meaning of this expectation of x is 15? What does this mean? It means that if you try, okay, if you try many times, okay, sometimes you may be just coming out after 3 hours, sometimes you may be coming out after maybe 15 hours, sometimes maybe after 25 hours, sometimes after 50 hours, sometimes after 100 hours maybe you are coming out. But if you try it, many times, then on average, okay, on average you will be, or the miner will be coming out after 15 unit of time. Okay. So this is on average. On average means what? Means average of how many experiments? Average of how many experiments means that first time you do experiment, you come out of the mine after 3 hours. Second time you do the experiments, you come out of the mine after, let's suppose, 100 hours. So after how many experiments I can say the expectation will be 15. I mean, this average in terms of the expectation, we say after how many trials. In how many trials we can get this expectation? Theoretically theoretically basically infinite number of trials, right? The expectation is defined like this only. So if you try large enough experiments, then you will be getting 15 as an average, right? Do you remember this? I think in one of the lecture I gave you the example of the gambling. Let's suppose you are having some gambling game in some casino, and then you are trying your luck, and suppose you lose the money, then and the probability of winning is, let's suppose, 1 by 3 or something like this, right? So if the probability of winning is, let's suppose, 1 by 3, then does this mean that after 3 trials you will be winning? No, right? So basically, it's like that. It's like that if you try enough number of times, then 1 by 3 number of times you will be winning. This is the definition of probability. Similarly, we have told you the definition of this expectation means if you try enough number of times, Okay, if you try enough number of times, then on average you will be coming out after 15 unit of time, right? Okay. Now, let's see this law of total expectation little more formally. Okay. So basically, this is actually the law of total expectation only, but we will see little more formally, which means, which means if you want to find out the expectation of, let's suppose, any random variable, let's suppose x, then what you can do, you can say that, okay, you can divide it into the events. For example, let's suppose y is some, random variable and y equal to 1 is one event, right? So let's suppose these are the three possible events only, okay, with respect to y. Maybe y value can be 1, can be 2, or can be 3, right? Let's suppose, which means either you choose door 1, door 2, or door 3 in this particular case. But yeah, uh, but in general, let's suppose you want to find out expectation of any random variable, then what you can do, you can divide the sample space into the events, and you can say, okay, if this occurs, then what is the expectation? If this occurs, then what is the expectation? If this occurs, what is the expectation? Okay, and then we call this particular thing as law of total expectation. So what do I mean by that? Let me just show you. See, let's suppose x is a random variable and we are interested in finding out expectation of x. Then what we can do, we can divide our sample space um, into, let's suppose, n events, which are called partition. Do you remember the meaning of partition? What does this partition mean? This is actually, sad theory term. Okay, if you don't know or don't remember, then it is fine. But has anyone noticed that I already told meaning of partition in the first module? Yes. So it is mutually exclusive and exhaustive, which means you are dividing into n events such that no two events are overlapping, and then all events are basically giving you the sample space, right? Okay. So basically this is called partition. Okay, this is called, okay, mutually exclusive and exhaustive, which means no two events are overlapping. This is called exclusive, mutually exclusive, and exhaustive means all of this together forms a sample space, right? Okay, anyway, if I divide the sample space into n partition, then I can say expectation of x. Okay, expectation of x is nothing but probability of event a1, and then if event a1 is there, then what is the expected value of x? If event a2 is there, then what is the expected value of x? Like that, right? So we call this whole thing as a law of total expectation. Okay. Yes. So Sonam is also writing the meaning of partition. Okay. So is this little bit clear that what I'm trying to say here? Law of total expectation. See, you have already solved these kind of questions, right? We have already solved in the module one also. Now I'm just defining it little more formally because it is needed for gate DA. Okay, module one was common for gate D and gate CSE. Okay, so that's why like we have not went to much further details, but yeah, in the module two we will see more formally. Okay, so see here what I'm trying to say. If these are the disjoint events that forms a partition with, let's suppose, the probability is greater than zero, then you will say the expectation of x will be, you will be dividing into n partition, then it will be probability of a1 into expectation of x given the a1, right, plus probability of a2 into expectation of x given a2, like that. So basically, what we have done, we have already solved these kind of questions, but now we are defining it. Now we are defining it more formally, right? So let's just see more examples. Suppose I say you that find out the expectation of x, where x is the number obtained while rolling a die. Then can you do it? Maybe just like the usual way. So I think you can do it. Let me just tell you that how to do it using the usual way, which means, what do I mean by usual way is like this. So what I'm trying to say, that if x is number obtained by rolling a die, then what is the expectation of x? You will be saying it is nothing but that either this is summation of x into px, right? So you can say either one can appear. If one appears, then probability is 1 by 6. Or two can appear. If two appears, then the probability is 1 by 6. Like that, right? Or six can appear, then the probability is 1 by 6. This is very well computed number, we already know this is coming out to be 3.5. So is this fine to everyone? How to find out the expectation? This is easy, right? But let's just find out the same expectation using law of total expectation. So what I'm going to do here is that I'm going to divide the sample space into two disjoint events. Let's suppose A and B. Okay, just for the sake of understanding the thing. See, the answer is 3.5. You can do it in this way. That's not an issue. But I'm just telling you, let's see if we do it in this way. So what is the expectation of X? Can anyone solve actually in this way and then tell me what is the expectation you're getting? Okay. Don't solve in the usual way. Just solve in this way and then tell me what is the expectation you're getting. Which means divide the sample space, let's suppose, into two events, and then using those two events, use the total law of probability, okay, or law of total probability, and then tell me what is the expectation you're getting. Okay. Okay. You people might have tried it. Let me just tell you that what should be the answer, right? So this is nothing but expectation of X here is nothing but probability of A into into expectation of X given that event A plus probability of B into expectation of X given that event B. First of all, tell me, is this formula right or there is something wrong with this? Which means, are they actually forming a partition? If they're forming the partition, then this formula is right. Yes, they are forming a partition, right? There is no overlapping, there is nothing left, right? Like that, right? They're forming a partition, so that's why this formula is correct. There is no problem with this formula. So now let's just find out the probability of A. So what is the probability you get 5 at 6? 5 or 6 basically. So I think this is 2 by 6, right? Which is 1 by 3 or 2 by 6, right? Into what is the expectation of X given that A? Let's just find out this, right? What is the expectation of X given that A? So what you can do, you can work with the reduced domain. Okay, for simplicity, you can work with the reduced domain. So what is this expectation? What is the average of these two numbers? I think this is 11 by 2, right? So this is 11 by 2 plus, I think this is 4 by 6 into, what is the average of these four numbers? It is, I think, 10 by 4, right? Okay. So now this 2 and 2 will get cancelled out. This is 11 by 6 plus this 4 and 4 get cancelled out. This is 10 by 6, right? This is 21 by 6. Okay. So what is this 21 by 6? I think this is again 3.5, right? So you can solve in any way. I mean, that's not an issue. You can solve in the previous way, the way we have solved. This is easy, obviously, but you can solve in this way also. I'm just trying to show you a small example where this law of total expectation is being used, right? Okay. Is this understood to everyone? Okay. Now let's just see more questions, right? So I think here we are getting 2.5, 3.5, which is fine. Now let's just see more questions. Let's see this question. Okay, so what they're saying, this question, by the way, I've taken from MIT. Okay, so this is a good question which I've taken from MIT. I don't remember if this question has already been taken in module 1 or not. I don't exactly remember. Do you remember if this particular question, exact same question, if I've taken in the module 1? Oh, exact same I've taken, because now I feel like I might have taken. Okay, not an issue. But here we will see it. Oh, similar type I might have taken, but exact same question I'm asking. Okay. So let's see what they're saying. They're saying that you pick a number between 1 and 6, then you roll three fair independent dice. Okay. So you pick a number between 1 and 6 first, and then you roll three dice. If your number comes up, then you lose $1. Okay, we are rolling three dice. If your number comes up once, if your number never comes up, then you lose $1. If your number comes up once, Okay, then you win $1. If your number comes up twice, then you win $2. If your number comes up thrice, then you win $4. What is the expected payoff? Okay, so this is interesting. Let's just try to solve this, right? So what they're trying to say is that you first pick a number between 1 and 6. Okay, and then you let me just write bit more that what they are trying to trying to say, and then I want you to solve this question for just few seconds, and then we will be solving, right? So your number, the number that you are going to pick is from 1 to 6. I mean, one number you are going to pick from 1 to 6. So this is basically the first task that you are doing. And then let's suppose your number is 4. Okay, then you are rolling, okay, dice 1, dice 2, and dice 3. So basically you are rolling 3 dice. And now if your number is coming, okay, in the dice 1 and dice 2 and dice 3, I mean in all of the dice, then you are winning $4. If your number never comes up, you are losing $1. Okay, if your number comes up at least once, then you are basically winning just $1, like that. Do you want to try this question? So this is little, tricky question might be. Let's just try solving it. So suppose that they're asking you expected payoff, right? Maybe you are losing, maybe you are winning, right? We don't know. Let's just see. Okay. Let's suppose that they're asking you to find out expected value of, let's suppose, some random variable r. Okay, where r is the payoff. So r is the amount that you pay. Okay, or you win or lose. Amount you win or lose, right? R is the amount that you win or lose. Let's suppose, right? Okay, sorry. Now, expectation of r will be the expected amount that you are winning or losing. So what it will be? Let's just try to formulate it. So you are winning, or maybe you are losing $1, which means -1. If the number never comes up, right? If the whatever is the number you are choosing, if that never comes up, then you are losing $1. So you can say that here, if never comes up, plus you're winning $1 if it comes once, right? Probability of, if your number comes once in any of dice, right? Similarly, similarly, plus it will be 2 into probability of number uh, comes twice, right? Comes twice, because then you are winning 2, plus you are winning 4 if number comes thrice. Okay, so this is the formula that we are getting. Okay, so let me, yeah, they are also solving in the same way. Maybe I can do one thing. I can just copy it for the sake of, saving the space. So, instead of writing with my own handwriting, let me just write in the typed fashion. Okay. Yeah. So basically, this is the expected amount that you win or you lose. Now, how to calculate these probabilities? This is the question. The probability that the number that you are choosing, right, is basically having zero match. I mean, it is not matching with the any of the dice. So basically, what you can do here, you can try to understand like this. Okay, you can try to understand like this, that this probability you can marginalize, which means that the probability that it match zero matches, right? So let me try to find out this probability separately. So this is probability of zero match given that you choose one, right? You choose one into probability of choosing one, plus the probability of zero match you choose two into probability of choosing two. Probability of choosing two. Is this okay to everyone? And dot dot dot. So what is this first probability? Probability of choose one is 1/6, right? And if you're choosing one, then there is no match. What is the probability of there is no match? If one doesn't come in any of the place. So if one doesn't come in the first dice, then this is the probability 5/6. It doesn't come in the second dice and the third dice. So I think this is the probability, right? So basically, this is the probability that one doesn't come neither in the first, second, and third, right? And choosing one is this probability. Similarly, you will do it for two. So basically, for two also, this is the same probability, right? Into 1/6. For three also, this same probability. So these are the six such numbers. So finally, what is the answer? So basically, it is just a lengthy way, but you can rewrite it as 5/6 cube, right? So basically, what I'm trying to say here is that probability of no match, okay, whatever is the number you are choosing, actually due to symmetricity, it doesn't matter whether you are choosing 0, 1, 2, or 3, or whatever, right? Probability of no match, whatever number you choose, right? So the probability of no match, and neither it matches with the neither it comes in the first dice, nor it comes in the second dice, nor in the third dice. So this is the probability. Okay, whatever number you choose. If you want to write it, this total log probability way, then you can do it. Otherwise, you can directly understand that the probability that whatever number you are choosing, it doesn't really matter. You can work with just one number. Okay, actually, you can just work any of the number. Let's suppose you choose any number, which is let's suppose one. Okay, then you can do this calculation just based on chosen number one. Okay, why? Because you can understand like this. Maybe you can understand like this. See, you might be choosing one of this number, right? Let's suppose you choose one. Okay, just log it. Okay, just log it. Now find out, if you choose one, then what is the expected number of amount of money that you are losing or winning? Let's just find out this. Is this fine to everyone? Okay, now we are not going to change our number. One is fixed. Okay, let's just do it in this way. Maybe you will try to, maybe you will understand better. So the one is fixed now. Now I will not say that, okay, what if I choose two, what if I choose three, like that, right? Let's just lock it. So one is fixed. So what is the formula here? This is the formula, right? Now, okay. So if one is fixed, then in that case, if you lock it, okay, just freeze it. Just freeze it. Let's suppose you choose one. Then what is the probability that there is no match? I mean, one doesn't appear in any of the place. What is the probability? That one doesn't appear in dice one doesn't appear in dice two, one doesn't appear in dice three. So if one doesn't appear in dice one, and one doesn't appear in dice two, and one doesn't appear in dice three, this probability, right? Okay. Plus one into one match. So which means one appear in exactly one dice. So what is the probability? This is interesting. This is the probability probability that one appears in exactly one dice. So, so this one is because of this number. Now, let me tell you the probability that one appears in exactly one dice. So it might appear. See, there are 3C1 cases, right? It might appear the one might appear in first dice, second dice, third dice. This is the binomial distribution, right? So this is 3C1 into appearing is 1/6, right? 1/6, and if it doesn't appear in remaining dice, then it is 5/6 square. Okay, so it is 3 into 3C1 into 1/6 into 5/6 square. Okay. Now, similarly, one appears in exactly two dice, then 3C2 or 3C1, actually 3C1 or 3C2 are same. Exactly two dice, which means 1/6 square this time into 5/6, right? Okay. In exactly three dice it appears, or all of the dice, then 3C3, or you, if you don't want, you don't write anything. 3C3 just one. Okay. Or maybe you can write 3C3. So basically, it will be 3C3, right, into 1/6 cube. Is this fine to everyone? Okay. So if you solve this, you will be getting minus 16 upon 216. Okay. So if you solve this, this is minus of 16 upon 216. This is the number. Do you want to cross check it? So how much this is? Minus 1 upon, I think this is uh, 11, or how much? So 216 divided by 16. Sorry, this is 13.5. Anyway, so this is not the whole integer, but that's fine. So minus 16 upon 216. That's what you're getting. Now, is this the answer? Or this is the answer only when we are getting one? So if we are getting one, then this is the on average that you are winning or losing this much amount, right? Now, what if you get two? What if you get two? Do you think anything will change here if I log two? If I log two, do you think anything will change? No, right? So if you log this two, nothing will change, right? So which means, so nothing will change. So which means that let me call it ER2 if you want to. Okay. This is the amount that I will be winning or losing if I log 2. Let me call it ER1. The previous one, let me call it ER1. This is the amount that I will be winning or losing if you log 1. Okay. This is the amount that I will be winning or losing if you log 2. Similarly, if you log 3, then maybe the similar amount, right? The similar amount you can say. So if you log 3 also, then the similar amount you will be winning or losing. There is nothing that is getting changed. Okay. So if because of the symmetricity, what you can say, the expected number of amount that you will be winning or losing is nothing but you may choose one. Then what is the expected number of amount you will be winning? You may choose two. Uh, Sorry. If you choose one, then this is the probability and this is the amount, expected number of amount. Yeah. So I think this is correct. Now you may choose two, right? And this is the expected number of amount that you will be winning or losing. Similarly, and so on, right? You may choose six, then this is the expected number of amount, let's suppose, that you will be winning or losing, right? So one of this quantity is minus 16, or let's suppose that's let's suppose x, or let's suppose t or c or whatever, right? So let's suppose this is c. Okay, so everything is c basically. So this is 1 by 6 c plus c plus c plus c plus c 3 4 5 6, which is just 6c by 6, which is just c, which is just nothing but minus 16 upon 216. So basically it is the same amount, right? I mean, you choose one, you choose two, it is the same amount that you are getting. So it doesn't really matter which what you choose. Okay. So you choose one, you choose two, you choose three, you will be basically paying off this much amount, right? So similarly, on average, you are paying off this much amount. So actually, because of the symmetricity, you don't need to worry about one, two, or this three, six individually. But if you want, you can have more clarity like this. So you might have noticed one thing. What kind of formula we have used here? This is called law of total expectation, right? This is called law of total expectation. Okay. Now, here, here, what we could have done, okay, instead of using, basically what I did here, I logged one. And then I'm saying that, okay, now let's just find out the expectation. Okay. Instead of that, what you can also do, you don't log anything. Okay. You just find out this directly. If you find out this directly, then in finding out probability that nothing is matching, then in that case, I'm having different cases. So I'm using here what kind of formula? Law of, can anyone tell me? Total probability, right? If you don't lock it, then you can use law of total probability like this. If you're locking it, okay, if you're locking it, let's suppose you're locking on one or two or something like this, then you can use law of total expectation later on. So I will suggest this way because it won't confuse you. Okay. So if you don't lock it, then you might be getting confused that, okay, probability, what if you get you choose one, what if you choose two? So let's just fix it. Okay, let's just fix this. That let's suppose I choose one, then let's just do all the calculation. Okay, and later on, for your own satisfaction, you can use law of total expectation, which means, okay, what if I could have chosen two, what if I could have chosen three, like this, right? Actually, it is not needed, but just for your sake of satisfaction, if you want, you can do it. Are these both methods clear to everyone? What I'm trying to say, right? So here, currently, I'm not locking it. I mean, in this particular method, I'm not locking it. I'm just saying, okay, maybe let's just find out this quantity directly. Okay. And in another method, I'm finding out, for example, ER1, R2, R3, like this. And then ultimately, I'm using law of total expectation. Okay. Cool. So by the way, looking at this game, okay, looking at this game, what it might be coming to your mind. Okay, you are losing only at one only in one case. What is that case? If your number never comes up, isn't it? You're losing only in this case. In remaining case, you are winning. So it seems like on average you will be winning, isn't it? I mean, it seems like intuitively it seems like that on average you will be winning because you are losing just in one case, okay, and in all the cases you are winning. So, but our mathematical calculation is showing us that on average, you will be actually losing, right? So basically, like if let's suppose any of the casino is having this kind of games, then on average they will be just earning money. Okay, they will be not losing money. So, for example, let's suppose there are 100 people that are playing per day. So, in a month, let's suppose 3,000 people are playing. In a let's suppose 6 months, let's suppose 18,000 people are playing, or in an year, 36,000 people are playing. So, in an year, they have enough data. 36,000 is, I think, enough data to justify this expectation, right? So, on average, every person will be losing this much. So this much into 36,000, that much they will be winning on average, right? Okay, that's what this MIT PDF also say, that you can expect to lose this much dollar about they have converted into another currency, about this much cents in every round. This is a horrible game. Okay, so it seems like you will be winning, but ultimately you are actually losing. So that's why mathematics is useful. Okay, can anyone tell me what does this expectation again mean? What does this intuitively say? If you want, you can just speak up and let me know. What do you think? What does this? What is the intuitive meaning of this? Anyone wants to talk about it?
Good morning, sir.
Hello, Sonam. Yeah, good
Uh,
morning.
it means on an average how much amount I'm losing if we perform lot of trials.
Yes, right. So if one person perform lot of trials, then this is the amount you will be losing. Or maybe you can say in other way. Maybe you can say that if instead of one person performing these many trials, if let's suppose multiple persons are performing trial, then everyone will be losing. I mean, on average, they will be losing basically this much amount. Yes, that is true. So basically, if you perform, you can say if you perform enough number of trials, then you will be losing this much amount on an average. Okay. So now let's just move to the next question. Let's solve this question. I think these kind of questions we have already solved in the module one also. I don't remember if the exact question was being solved or not, but let's just solve this question again. Okay. So what they are saying that find out the expected value of what is the on average we are returning. For example, let's suppose y is the return value. Then what is the expected return value? This question I have taken from Stanford University. Okay. So this is the Python code. You might not be aware about the Python code, so let's not worry about it. This is just a pseudo code. You can understand that x is some random number chosen from 1 to 3. If x is 1, then they are returning 3. If x is 2, then they are returning 5 plus they're actually recursing on this. Otherwise 7 plus they are recursing on this. Hint is also given here. Okay. So what they're saying that if y is the return value, then what is the expected return value? So you can say the expected return value will be, if you choose one, the probability of one, then if you choose one, then what is the expected return value? If I mean if this x is coming out to be one, then what is the expected return value? If x is coming out to be two, then what is the expected return value? If x is coming out to be three, then what is the expected return value? Right? So I hope you can solve this question. So what is the answer here? So here, yes. So Diksha is saying 15 and 15 is the correct answer. Yes. Okay. Okay. So is this fine to everyone? Okay, great. Now, let's just solve more questions. Okay. Okay. Let's just solve one property and then we will solve more questions. So here you might have observed one thing. Okay. So here, for example, in any of the case, you might have observed one thing is something like this. So basically, if you're finding expectation of any number, let's suppose y, then this is the probability of x being, let's suppose, 1, and then expected value of y when x is 1, something like this, right? So maybe I can just copy it and then I can just show you something, okay, that I want to show. So suppose, hmm, So let me show you that what I'm trying to say. See, whenever we find out the expectation of any random variable, then in these cases, we are using law of total expectation, right? This is also called as actually law of iterated expectation or total expectation. Okay. There is one more way of writing this law of total expectation. So basically, till now, you can say that we have been saying something like this. Okay. Till now, we have been saying something like this. So here, this is suppose just expectation of x. Is this formula correct to everyone? Is this formula right? Does this formula make sense to everyone? The expectation of x is equal to this much, right? Does this make sense? Okay. Now, so basically, now what I'm trying to say here is that we are saying this is same as something else also. Okay, I mean just a way of rewriting it. Okay, see here, see this is actually this is expectation of, you can say, let's suppose y value is 1 and 2, or maybe 1 2 and 3. So you can say maybe summation of, or let me write in the let me open the summation. So it will be expectation of x y being 1 into probability of 1 plus expectation of x y being 2 into probability of 2. Let's suppose there are only two values of y. Okay, there are only two possible values of y. Okay, so is this fine till now? Till now, is this fine to everyone? That's what we have already seen, right? Now, what we are going to do, we are going to just realize one thing here. Okay, just a notation wise. Okay, just a notation wise. Tell me, tell me, if I treat this, okay, if I treat this whole thing as just one random variable kind of thing. Okay, for example, for example, let's suppose I treat this whole thing as g of y. Okay, some random variable, some function of random variable y into probability of y being 1 plus, I mean, you can say g of 1 basically, that doesn't matter. So g of 1 basically, okay, here y is actually 1. And similarly, g of y, here actually y is 2, but I'm just writing like this, okay, probability of y being 2. Can I write like this? Okay, I'm just treating this thing as a function of a random variable y. Okay, just to have some notation. Okay, so there is nothing much discovery that we will be doing. It's just a notation wise, actually something is there that I want to convey. Okay, so basically, you can say, interestingly, you can say this is nothing but expectation of gy. Is this okay to everyone? Tell me, right? And what is this gy? Gy is nothing but, tell me the value of gy. It is nothing but the function which is telling you the expectation, right? Isn't it? Okay. Don't worry if it is like looking little complicated. But actually, what I want to convey here is that this particular thing, which we have been calling it as expectation of x, right? Expectation of x. You can also call it expectation of x given y. Okay. So basically, expectation of x, we have been calling it, which is same as expectation of x given y, which is same as summation over, or maybe I can just copy paste it. So basically, see, what I'm saying here is that this particular thing was known to you, right? This particular thing was known to you. I'm just saying that this thing is also equal to this thing. Okay, it is just a matter of seeing the things differently. So see, this is what we already know using the total of expectation, right? Now I'm just saying this particular thing, if you treat this as a random variable, obviously you can treat it. Maybe I think in the previous class itself we have discussed about it, right? So this is, if you can treat this particular expectation just like a random variable g of y. Okay. If you treat this as a random variable, then this is the expectation of this quantity, isn't it? See, what is the expectation? Expectation is nothing but expectation of any quantity, okay, for that matter, is nothing but expectation of any quantity is nothing but whatever is the quantity, that quantity, let's suppose this quantity, okay, whatever this quantity, right, into probability of, let's suppose, maybe should I be using some function? Okay, let's suppose this is x, for simplicity, let's suppose this is x, right? So x being 1, so this is basically x being 1, probability of x being 1, plus if x is 2, then probability of x is 2, like this, right? Similarly, for any other function, expectation of any function g of x is nothing but, do you remember there is one law, and anyone, can anyone tell me what is this law called? The short way to find out the expectation of function of random variable. What is this law called? Okay, let me give you some hint. No. Law of unconscious, something like that. Yes. So that we used to call it lotus, right? Okay. So basically, it is nothing but, if x is 2, then 2 g of 2 basically, g of 1. If x is 1, then g of 1 into probability of x being 1 plus g of 2 into probability of x being 2, right? So that's what I'm saying. So expectation of any function is nothing but that particular quantity into x equal to 1, like this, right? Now, similarly here, I'm just trying to say that if you are writing, okay, if you are writing expectation of x, y being 1 into probability of, let's suppose, y being 1 plus, okay, if you're treating this as g of y, isn't it the expectation of g of y? Tell me, isn't it the expectation of g of y? Right? So expectation of any quantity is nothing but, expectation of any quantity is nothing but the probability of, let's suppose this is a function of x, then probability of x being 1 into g of 1, like this, right? Plus probability of x being 2 into g of 2. So if you're writing something like this, okay, then can't you look at it just like the expectation of this quantity itself? Can't you look this formula, okay, as a expectation of this quantity itself? There is nothing wrong in this, right? It's just a way of looking. Is this way of looking fine to everyone? Okay, I know it is not very intuitive. That is the reason that I haven't told you in the module one. Okay, in the module two, we have to actually touch more mathematics. Okay, there is no other way. Because it is gate DA, so just expect it to have mathematics. Obviously, right, in the gate DA, you will be having little more mathematics than the computer science lectures. So basically, in the gate DA, these things will be little more, you can say the mathematics will be little more often. Okay, so just get used to of this. So this particular, you can say this particular quantity, right? You can look at this quantity as an expectation of this quantity. Okay, expectation of which means this random variable. Okay. Okay. Now let me ask you about something. Let's suppose if you are writing expectation of uh anything, okay, maybe expectation of, let's suppose, x only, then maybe you are saying this is x being 1 into probability of, x being 1 plus 2 into probability of, let's suppose, x being 2. If you're writing expectation of any random function of random variable, then you will say it might be, okay, you will say it will be basically. Do you remember this? If you remember, I told you that if you're finding the expectation, then then this thing will never change. Do you remember that you can keep on substituting here and there, but this will not change? How many of you remember that I actually circled like this in the module one itself? I must have done like this, right? In the module one itself. How many of you remember? Okay. So basically this thing will not change. Now, suppose I ask you that this is the expectation with respect to which probability distribution, then you will say this is with respect to the probability distribution of x. Suppose suppose I ask you to find out the expectation of the same quantity gx. Okay, but this time I ask you to find out the expectation with respect to, let's suppose, okay, let's suppose the with respect to some other random variable, some other probability distribution, which is gy. Okay, so here you will say this is g whenever this, okay, so this will be p of, you can say, x being y, right? um Sorry, let's suppose I ask you to find out the expectation with respect to another probability distribution, which is a probability distribution defined for the random variable y. Then you can also write like this, okay, which is fine. And now suppose x and y are independent. In that case, let's suppose that x has nothing to do with if y is changing, y is not changing. It has nothing to do with that. So it will be just gx. Why? Because gx you can take outside, and this particular quantity is just one, right? So anyway, what I'm trying to say here is that expectation, whenever you are trying to find out, it is with respect to some probability distribution, right? Okay, cool. So here, here, are you convinced that that let me just tell you again that if you are writing expectation of x, then you can say this is nothing but expectation of x given y equal to 1 into probability of y being 1 plus expectation of x given y equal to 2 into probability of y equal to 2. Is this okay to everyone? If y values are, let's suppose, possible values are only 1 and 2, which is nothing but expectation of, okay, so don't get confused with these two expectations. Just treat it like a number. Expectation of this particular quantity, right? So expectation of this particular quantity, which means, isn't it? Let me know. Okay. Okay. So by the way, tell me, this expectation is with respect to which probability distribution? I mean, you made it a short formula, but this is with respect to probability distribution of y, right? I mean, here y is changing. So this is, you can say, with respect to y. This expectation, so this is the same thing, right? This is the same thing. I mean, this is the same expectation. So this expectation here y is fixed. But if you find out the expectation of x, then it is, if you open this up, then if you remember, then expectation of x given y equal to 1 is nothing but summation over all the possible values of x, right? Probability of, you can say, x given y equal to 1 and then x, right? Something like this. So this is, you can say, with respect to x, right? Because you are basically summing over all the x. Anyway, it's not important, but I'm just telling you, okay? It's not much important, but I'm just telling you here. Okay, the more important part is that you should understand that these three things are same, because they might use this notation. Okay, that's why I'm telling you, they might use this notation. because this is popular notation. Okay. So if they use this notation, then just treat it like expectation of x only. That's the only takeaway that I want you to understand. Okay. Maybe you can understand little bit more using some, you can say, examples. Okay. So maybe let's just first solve this question, and then we will solve some true false examples, after which you will be more clear that what I'm trying to say. Okay. So what they're saying, that suppose x and y are two random variable. Okay. Suppose x and y are the two random variable. Now let's suppose instead of gx, for example, let's just have x for the simplicity. Now they are saying, if you are having, okay, the if you want to find out the expectation of, let's suppose, expectation of x into some function of y given the x. So they are saying expectation of x into some function of y, hy or gy or whatever, let's suppose gy, given x equal to maybe 1, x equal to 2, or like that, right? Anything, okay? X equal to c. Then this is nothing but, you can say, c into expectation of, okay, suppose this is the thing that I want to show. Okay, for example, suppose this is the thing that I want to show, which means they are saying, if you want to find out the expectation of, let's suppose, this gy given that x equal to some value, right? I mean, so we have been using this notation, x equal to c or like that, right? We have been using this kind of notation. Now they are saying, let's suppose instead of by, okay, not just by, you have gy, which is fine, but you also have x with this. Then actually x is known to us, right, which is c. So you can substitute the c here, and then this is constant, so you can take it out. Okay, is this okay to everyone? This is not very hard to understand. Is this okay? That what you can do, you can substitute the value of c, and then you can just take the c out, right? Okay. So basically this is called as taking out what is known. I mean, this is not a very popular term, but I'm just telling you. Okay, some author use it. Taking out what is known, which means if x is known, you just take it out. Okay. Now, if you want to represent this in terms of function, okay, instead of c, if you want to represent this the same thing in terms of function, then what you can do, function in the sense, if you want to say that, okay, instead of c, I want to have the common name, which is just x, then you can write it like this. Okay, which is also fine. Which means expectation of x into g of y, given that x value could be anything, it is actually, you can take this x out. Okay, if x value is c, then you will replace x with c in the RHS, like this, right? So this way is also okay, which means here I'm putting x equal to c, but you can rewrite it as a function, which means you can say, okay, if x is taking the value c, then it will be c, like that, right? So I hope that is fine, right? This is not very complex. So this is one of the property, you can say, that we will be using to solve many questions. If you know the value of x, you can take it out. Okay. So for example, if I just ask you, okay, if I just ask you whether this is true or false, then what is your answer? Expectation of gx into hy given the x, is this true or false? See, the x is known, right? So you can take the quantity of x outside. Okay, so that's why this is true actually. Okay, so x is known, so we can take Basically it will be a constant, right? This will be the constant. Okay. Okay, for some x, for every x, I mean for some given value of x, this is constant, and x is given here. Okay, x is given for given value of x. Understood? Okay. Mhm. So now maybe we can do one, two more properties. So, and then we will be solving questions. Okay. So suppose that we have any, linearity of the expectation, which means let's suppose we have something like this. In that case, we can just like the previous case, we can just separate it out. Okay. So we can take this a1 out. We can just like the previous things. Okay. This is called linearity of the expectation. And if you remember previously, we have said that if there are two random variables, let's suppose x and y, r1, r2, or something like that, if they're independent, okay, if they're independent, then you can take this. No, I mean, you can rewrite it like this, that expectation of x into y. Okay, if they're independent, then this is expectation of x into expectation of y. Do you remember this? If they're independent, you can rewrite like this. Okay, if it is given a, then also that is fine. Okay. Now just tell me whether this is true or false. Just let me know quickly. Yeah, this is true, right? It is easy. This is true. Why? Because y is given to you. So for every y, this gy is constant. Whatever the value given is given to you, you can just substitute it here. Okay. So for every y, the gy is constant. This, by the way, this question I've taken from UCLA. Okay. Do you know about this UCLA university? It is one of the very popular university, one of the very prestigious university. I think current CEO, okay, of YouTube. Okay, current. I forgot her name. She is a female, basically. Current YouTube CEO is from UCLA only. Okay, it is very prestigious university, by the way. Okay, now let's just see this. X, Y, Z are the random variables. Then is this true or false? Tell me. So, expectation of expectation of X given by given by. Okay, this is little complicated. Just tell me. Okay, tell me, the below thing is true or false? This is, I think, true, right? We have been seeing it. This is true. Now you can definitely write in both the places in the expectation. Actually, you can definitely write this quantity given by given by. Okay, you can definitely write this. So this is also true. Okay, you can just write given by here, given by here. Okay, and then you will be getting this. Okay, tell me about this. This is true or false? Okay, this is EG, this is true, right? This is just a linearity of expectation. Tell me this. Okay, just see this. Is this okay? This is the total of probability, total of expectation, right? Okay. So this is total of expectation. Sorry, law of total expectation, I think, right? Law of total expectation. Now, if you write given B, okay, in both the places. So here given A is already there. So given B means that comma B, comma and intersection is actually same. Okay. So if you write given B in both the places, then you will be getting this, right? So instead of, you can understand like this, instead of working with the whole domain, you are working with the reduced domain. Okay. Given B, you are working with the reduced domain. So in the reduced domain also, it is fine. So that's why this is true. Okay. You're working in the reduced domain. So you can say this is law of total expectation in the reduced domain. Tell me, is this true or false? Yeah, this is true, right? If y is known, so we are taking out what is known, right? What about this? Do you want to try this as an homework? Okay. So just try this as a homework. Should I reveal the answer? Okay. It is actually true. Okay. So answer, let me write it. Just see why it is true. Okay. Just see why it is true. Just try to get convinced. Tell me this. So you can understand like this. This is expectation of x given that x is some value, right? C. So first write in the normal way, then you can write in the function way. So it is nothing but you can substitute it. So if this is known, it is just a C, right? Expectation of C given that x is C. So expectation of constant doesn't matter like given that x is C or not. It is just a C, right? Which is nothing but x. So that's why it is true. Okay, this is okay. Yeah, if Z is independent of X, then basically, if these two are independent, then it doesn't matter whether you are finding the conditional expectation or the normal expectation. This is also true. Okay. You can drive this. You can obviously prove it using the formula. So basically, you can write the formula of expectation of X, which is nothing but expectation of this conditional expectation, which is nothing but, you know, for the all possible values of X into probability of X being X given that Z is some constant, which is C, right? So basically this probability is nothing but probability of X being X. So that's why the whole thing is nothing but expectation of X only. Okay. Okay. Now just try this question and let me know what is the answer you are getting. Just try out this question. Okay, just try solving this question. It is not very hard question. It is just easy question only. So what they're trying to say that expectation of Z is you can say okay x1 x2 x3, or maybe if you want you can write it y into x3, okay, if you want it. Otherwise x1 x2 x3 is also fine, but in terms of y I'm writing, okay, which is nothing but, since y is known you can take it outside, right, into expectation of x3 given y, and then I think x1 x2 and x3 all are independent, right? Mm, which is independent of both x1 and x2. Okay, so x3 is a random variable which is independent. So they have not given the relationship between x1 and x2, whether they are dependent or independent, but it doesn't really matter for this question, right? So we know that this y, which is nothing but x1 and x2, x1 into x2, it is independent of x3, because they are saying that x3 is independent of both x1 and x2. But whether x1 and x2 are independent or not, it is not given, and it is not necessary to know also. Okay, so it doesn't really matter for us. But yeah, this is independent. So that's why you can say it is just expectation of x3. So I think we have used multiple properties here. What is this property called? Okay, I mean, not exactly, but we call it taking out what is known, right? So we are taking out what is known. And what is this property called? Independence property. Okay, so this expectation of x3 is given as 3. So this is 3y. Now, depending on the value of y, I'm writing as a function in the sense if y value is 1, then this is 3, y value is 2, then this is 6, like that, right? Let's just check it. 3y, right? So we're taking out what is known, and then x3 is independent of y. So you can write like this. Okay, they have also used y into x3. Doesn't matter. You can write x1 into x2 also in the same way that Sonam has done, right? Okay. So now you might have understood that how to solve these kind of questions, right? So this is, this is because expectation of, okay, Sonam is asking why 3, because the expectation of x3 is given as 3. Okay, this quantity is given as 3. Okay, no problem. So now you might have understood a little bit that how to, find out the total expectation, what is the notations and these things. But now let's just see the conditional expectation or the total expectation in case of contiguous. Okay. So what if you have the continuous case, which means continuous random variable? So till now we have been seeing the discrete random variable, but it is now time to see the continuous random variable also. Okay. So I think, before maybe you can solve these questions directly, but we can start this particular topic tomorrow. And even before, telling you these kind of questions, okay, you can do little more revision about the contiguous from the module one, or we can do one thing. Let's spend 1 hour, or let's suppose 10 to 15 questions in just solving PDF of the contiguous random variable, which means that instead of asking directly for the expectation, conditional expectation, let's just deal with this kind of formulation. Okay, what I'm trying to say here is that, see, if you want to find out the expectation, then obviously you need to deal with these things, right? So let's just do one thing. Let's just break it into two parts. Let's just have few questions where I'm just dealing with this, which means what is the marginal PDF, what is the joint PDF, and these things, right? And then I will come to this. So we can start this topic tomorrow, and then what I will do, I will first have questions where I will be only solving, okay, the joint PDF, marginal PDF, these things, so that you are more comfortable with this joint and marginal PDF. And then we will be solving questions related to conditional PDF and conditional expectation and something like this, right? Total expectation and these things. Okay. Cool. So we will be starting this topic tomorrow. For now, what you can do, since you're a little bit familiar about the conditional expectation, joint PDF, and these things, these are the 2 3 questions with the solutions. So do you want to try these 2 3 questions? You can solve. You can see the solutions on the next page. Just try these 2 questions. Okay. This is question number 1 and question number 2 as an homework. Okay. You should be able to do it ideally. Okay, with the knowledge that you have. But still, since we have not done much practice about this PDF, neither in module 1 nor in module 2, so I'm thinking that we can have one dedicated class Okay, just to have more practice about the PDF. Okay, joint PDF, marginal PDF, these things. Because in the contiguous module 1 we have not spent much time. The reason was that the module 1 was common to gate cs and gate da. So in gate cs actually they do not ask anything from the contiguous. They rarely ask some question from the contiguous case. So that's why I don't want to overburden them, okay, gate cs students. So that's why I haven't told this contiguous case in the module 1 explicitly, I mean in much detail. So here let's just spend one class just to deal with this PDF explicitly, and then we will be dealing with the conditional expectation, conditional variance in the both of the cases, like which means the discrete and the contiguous. Okay, so you can do this question and this the next question that I have here as an homework, just for the sake of your own practice. Anyway, we will be doing it again. Okay, and solution is on the next page. Cool. Just definitely try it. Okay. Don't skip it. After you can see the solution. Okay. Just try it for few minutes and then you can see the solution. But don't skip the homework. Okay. Just try it. See, if I'm giving the homework, then I'm giving based on the thought process that I know that you can solve it if you try it. Okay. If you can't even solve it, even if doesn't matter how much hard you try, then why will I give that particular question as an homework, right? So I will not give if I know that you won't be able to solve with the current knowledge. Since I know that you should be able to solve with the current knowledge, that's the only reason I'm giving these two questions as an homework. Okay. Okay, so we will be starting this contiguous case in the next lecture, and then we will be doing lot of practice in the contiguous case PDF, and then these things, conditional expectation, these things will be just a cakewalk for you. The reason is that this conditional expectation is nothing but dealing with the joint distribution. For example, this conditional expectation, we will see it. It is nothing but dealing with the joint PDF and the marginal PDF, these kind of things, right? Once you have good practice about these joint and marginal PDF, then it is easy to solve conditional PDF, conditional variance, and these kind of things. Okay. So basically, there are a lot of things that we will be learning in module 2. Uh, so the things like that, like covariance, correlation, conditional variance, variance, more details about the variance, covariance matrix, right? There is something called covariance matrix, which is useful in the machine learning also. So covariance matrix, eigenvalues of covariance matrix, these things. So many things will come, okay, in module 2. And let me just tell you that probability is not as intuitive as linear algebra, which means linear algebra module 2 might have been interesting, might have been little more intuitive. But probability, by the nature of the subject, okay, it's not like that I'm teaching badly or someone else is teaching badly or something like that, right? It's not like that. It is by the nature of the subject, it is like this. So it is having less intuition and more calculation like this. Okay, so linear algebra is more intuitive than probability. So don't compare those subjects that okay, linear algebra has been taught nicely and probability has not been taught nicely. It's not like that. It is the nature of the subject by which it is hard or easy. Okay, so but still we will be having many questions as in practice, and make sure that you are very comfortable with all of these concepts, right? Okay, sure. Thank you so much.